Good evening. Hello, everybody. Welcome again to this new lecture. Today, we're gonna please remember to write your name and ID in the chat. I just want to point out that I posted a new recording today, a short one, 8 or 5 minutes. You can scroll through it real quick. I posted it today, an hour or two ago, where you find our class recordings. I called the recording, what is it? I called it Wiring the Electromechanical Relay, where I explain how to wire the electromechanical relay we mentioned last time, okay? Because I was watching the recording of last lecture, and I discovered that I was talking, I reversed the pins, okay? So this one has a detailed explanation on how to use the electromechanical relay. And we finished chapter 7. Before starting with chapter 6, I'd like to start to break the ice with you on using C. I know you have got some assignments on using C in the lab assignments, but I'd like to do it with you together today real quick. Do a simple application using the 7-segment display, something like counting. Just display the numbers from 0 to 9 forever, counting on the 7-segment display on our HCS12 microcontroller. So I'm going to start with that, with a C demo, C example, and program the HCS12. And you can use it as a test for your board. Make sure your board on the exam day is working, okay? Because I may give an asynchronous question or two that you will be asked to use your hardware. So let's do this. Let's make a counter that counts from 0 to 9 forever and display it on the 7-segment display already built in connected to port H on our microcontroller HCS12. Of course, we can, if we get an external one, we can wire it, but this is already wired for us. So I'm going to create a new project, select our family microcontroller DG256B. And you all saw last time I shared with you the news that NXP decided to extend the longevity of this microcontroller until 2031, and 10 more years. It's going to live for 10 more years for its wide use and importance in the automotive industry and other industries. Here we select C. In the previous examples we used to use assembly. Now we're going to use C. Later on, I'm going to give you, I don't know, something. It will include a tutorial that you will use both C and assembly. But now we're going to use C. And let's create, this is class demo going to be number 5, right? So 4 or 5, yes. So let's create a folder, call it class demo 5, and save the project here. Next, nothing to add. Next. Here I want to talk about these options. Do we want this wizard to create some startup code for us? The ANSI compliant code where some initializations of global variables and how to start the main subroutine or function, or the minimal. We're going to use the minimal. We need minimal help from this wizard. The only thing that's going to happen here is initialize the stack pointer for us. Okay, so we can so we can use functions basically and interrupts. and it will call the main function. For this, these three options, what kind
لو
of...
سمحت ممكن اسال سؤال؟
تفضل يا يزيد.
هسه لما نختار البرنامج وكذا، في مرات ما بيطلع لك كل الفاميلي تبعها، يعني مثلا فاميلي دي مرات ما بتطلع لي.
You can use P. بس يعني if you install the version I showed you.
انا نزلت الفيرجن الموجود على eLearning.
Well, anybody had the problem Yazid has? You need to make sure that you selected HCS12.
يس بس فاميلي دي ما لقيتها يعني.
No, it should be there. Are you sure?
شيكت مع الشباب مع
Can somebody confirm مين who's with us?
دكتور أنا كمان نفس المشكلة عندي.
طيب who installed it and used found family D?
أنا لقيتها دكتور موجودة.
أنا لقيتها دكتور.
يعني it's there guys. I don't know why it's not. يعني try to install or whatever. طيب anybody didn't find it and then found it يعني it's the same setup file. You want to stay until after the class show me, or I don't know. It's a software you set up. يعني
راح احاول دكتور ارجع اشطب وانزله من اول جديد ان شاء الله نفس.
It is there. طيب. Okay, for the memory model that shall be used here, let's choose the small memory model. If you choose the banked, we said, you know, there is a register called P page, and if you want to write code that is more than 64K, you go to pages, okay? So you use banked only if your code is so large, more than 64K bytes of code. The small means that our code is less than 64K. Let's use small. We're not going to use floating numbers. And finish. Start an empty project. What we want to do today here, instead of having the main.assembly, now we have a main.c. Okay, and we start writing our program. This is what we get. This is an empty. This is a skeleton. What we have is the includes, the derivative, which is our microcontroller derivative, where all registers are mapped to their addresses. You can check it. It is here and includes the DG256. Everything is here, all the registers. Just similar to what we saw in assembly. Okay, vectors, interrupt vectors, port numbers, addresses, and so on. We don't need to worry about them. Then a simple statement that enables the interrupts, a line. You can remove it if you don't want any interrupts. Well, this is equivalent to clearing the I bit in assembly, right? In the CCR code. And then we have the infinite loop here, the for loop. And in the infinite loop here, we feed the COP. The COP is computer operating properly, another name for something called the watchdog. And I told you what is a watchdog, did I? Somebody say, anybody confirm?
أول الفصل دكتور أتوقع.
Oh, we talked about a watchdog.
Yes.
Simply, it's a timer. If it overflows, it will cause the controller to reset. So we don't want it to overflow, so we reset it. We feed it here. There's a function that resets the watchdog timer. Okay, the watchdog timer timing, you can check it in the data sheet if you want to use it. You can configure it from a few milliseconds up to 2 seconds. Okay, long to cause the reset. It's not our core business today. Today we want to write something to display the numbers from 0 to 9 on a 1/7 display connected to port H in our HCS12. So what we want to do is the things that we want. We want first to configure port H as output. port. So it is so we can display write on it. Then we need to write a delay function, right? Because to see the numbers counting 0, 1, 2, 3, 4, you cannot just throw them to port H right after each other, right? You need some delay between them to be able to see them. We need to write a delay function. What else? Yeah, that's it, really. And we need to get the 7-segment map. The 7-segment map, before starting this lecture, I went to the chapter 4 here when we talked about the 7-segment display and just did this. Where is the 7-segment? And went to the table here on slide 28 and copied these numbers and I put them here for us. So 3F is 0, 06 is 1, 5B is 2, and so on. Okay, so they're for us to use when we need. طيب, yeah. So let's write our code. The first thing we need to do, let's write a delay function. We don't know how to do delays until this moment other than wasting time, right? Running instructions. This could be computed like when we did in assembly. We know the exact instruction, how long it takes. We're gonna just do some rough delay function today, then replace it later on with interrupts, real-time interrupts, okay? When we start using interrupts. So I'm gonna write a function called myDelay, okay? That just wastes time. It's not gonna return anything. This is the prototype. I'm not gonna pass anything. Okay, and let's write the function right after the main function here in the bottom. Okay, so what we will do is just waste some time. So if I do a for loop for I equals 0 to I less than, I don't know, 150 maybe, I plus plus, well, I in this case, and then here I need I to count until 150, so it can be, the data type can be a small data type, 8-bit, right? So I can say unsigned character. Unsigned character will reserve 8-bit in data memory. Unsigned means you don't need the 8-bit, the 7th-bit if we come from 0 for the sign. So you have the full 8-bit. So you can point for, you can count or hold a number from 0 to 255. Okay. If you just say character, then it is signed. Then in this case, you can count from minus 128 to plus 127 or hold a number in this range. طيب. And I'll need a larger one, a 16-bit number, an unsigned integer. An unsigned character is an integer, but 8-bit. Integer is a 16-bit, okay? Let's say J. And here, inside this loop, for I equals 0 until I is less than 150, it's just a number by trial and error, okay? Here, let me do another loop. So a loop calls a loop for J equals 0, J to J less than 20,000. That's why I made J as an integer, because integers can hold up to 65,536, right? I cannot hold this number because it is an 8-bit. Then J plus plus. And in embedded systems, we care about these details, right? We care about how our memory usage, our execution time, and we'll talk more about this when we talk about real-time operating systems. Okay, you don't have the luxury to just go book double for everything, okay? Your memory space, address space is limited. And here I just want to say مثلا I equals I for just wasting time any, and J equals J delay. Maybe that will do it. Okay, my delay. So there we have a function that just wastes time. Now we can start using it. طيب, what do we want to do in our main function? In our main function first, okay, we enabled interrupts. Let's keep this at the top. Before going into the main loop, I need to configure port H as output. So I say DDR H equals 0xFF, right? So here, port H is output. What else? I need the 7-segment map, and I can do this for the 7-segment map. I can define an array, call it, I can put it global if I want to use it somewhere else, or just keep it in the main function if I want. Maybe here, the first link. We can say define an array, an unsigned character, array of characters, yani 8-bit numbers, call it my 7seg, مثلا my 7seg array equals, and go copy those numbers I wrote here in Notepad. These, the 7-segment map. These are for common cathode though, for common cathode. And we know that our microcontroller is what? The 7-segment connected to the port H is common anode. Yes, Mustafa, thank you. So we need either, we either need to flip all the bits here, or just deal with these and do the ones complement when we write them immediately after writing them. And I'll do that probably, okay, to save time. So this is an array. 0x. 0x is equivalent to the $sign in assembly, okay? This means that this number is a hex number. Semicolon. What else? I need the counter to count the numbers that I want to display, صح? So we used already ij. Let's have an unsigned. We still can use I because it's a local variable, but anyways, unsigned character k. Okay, initialize k to 0. مبدئيا. What else? I think we're ready. We can start writing our code. What we want is what do we want to do? We initialized k. We want to say port H, write on port H, a 3F, 1K is 0, a 06, 1K is 1, 5B, 1K is 2, right? So I want these numbers in the array. So I say my 7seg, my 7seg of k is 0 initially. Then we can increment it. Now port H will get, when k is 0, the 3F, but 3F is the opposite, right, of what we want to display, because 3F is what we should write when we have a common cathode 7-segment display, but we know we have a common anode. I can in no time go flip all bits, make the 0 a 1 and the 1 a 0. So we can say port H equals tilde port H, and tilde here is the ones complement. Okay. So display the digit on port H. Okay. And here we are assuming the digit is common. We're displaying And let's write it here. These are 4 common cathode, right? Here we're doing invert all bits to work for common anode. طيب, now we'll see a 0 now. The 3F will be displayed to port H. Before incrementing and showing the next bit, the next number, the 1, we need to delay for some amount of time. So we call our function myDelay that we just wrote, right? Then we can increment K. And we need to make sure that the 7 segment is a 1 7 segment. We cannot go beyond 9, right? So we check if K equals 10, then we reset it to 0, right? And that's it. Then keep doing this forever. Looks good? Any questions, guys?
دكتور
Yeah.
هون لما كتبنا 10 ما حطيناها هيكس، تركناها انه without,
Yeah,
which is
the
decimal.
default here is decimal. Thank you, Talal. Yeah, the default here is decimal.
So it will be treated as decimal in this case.
Yes, and we're talking about a 7 segment display, right? يعني احنا what can we show on the 7 segment display numbers? 0 to 9. Well, if you want to show the A, B, C, D until F, we can extend this display, right? And then you're right, you will need to check against the F, which is, where is it? The if condition here. Yeah, you will need to check and against 0x, 0f, right? After f, well, which f? After 0x, 1, 0. If it's there, you go back to 0. Correct. But here, you need to add the digits for A, B, C, D, and F. Okay, I compiled here, no errors. It just gave me that warning here that you're assigning something to itself. I know, we're wasting time. So it's correct. Let me connect my microcontroller. Okay, choose full chip serial monitor. Sorry, reset my microcontroller, put it to the load mode, reset it before switching my camera. Okay, let me program it. Yeah, COM3, I remember it was programming. And now for a second, I'm gonna switch. This is done. Okay, I'm gonna hit this button. Okay, I'm not, but I want to switch my camera. I'm gonna disconnect voice from here and go to here. Okay, give me a second. Or I can just mute. You hear me, guys?
Yes, Doctor.
Yes, Doctor.
Okay, and you see my camera, my phone camera, right? I'm gonna hit the run button. Here's the board. Here's the board. Here's the 7 segment display. Nothing yet. I'm gonna go to my computer, hit the go button. I'm hitting it right now, and you start seeing the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then back to 0. Okay. طيب. طيب. Let me do this thing. See the numbers counting?
the speed is acceptable, right? It's like less than a half a second, something like that. What I'm gonna do now, I'm gonna switch the microcontroller to the run mode here. These dip switches to run mode, okay, and then hit the reset button here, okay. Now look at the numbers. 0. You see the 0, right? 1, 2. It is slower, it is counting, but is much slower. 4, and like 4 or 5 times, and there is a reason. Because I don't want to keep switching to hardware. I'll talk about this later. Mashi. So it was different when I hit this run button over here. When run button, the green arrow. Where is it? I'm sorry. Where's my mouse? I don't know if you see my mouse. The green arrow. Yeah, when I hit the green arrow here, the numbers were moving faster. Now they are slower. Let me go back to my computer.
Okay. Okay. Now you see me on the computer, right?
Yes, doctor.
The reason behind that the numbers were counting faster when I ran when I ran my program from here, when I hit this button, is that there are some initializations, or let's say when I hit the button, the setting here configures the PLL clock and changes accordingly the bus clock, and thus how fast instructions can run. Okay, but when we switch to running the code from there on, from the flash memory directly, the code of configuring the PLL clock is not there. We didn't write it, so it ran much slower. Okay, that is the reason. How do we make it faster? This is what we're going to cover when we talk about something called the CRG block, which is part of it is the it is part of chapter 6 that we're going to start shortly. Okay, but anyways, when our program we wrote, you know, this is our C code here, Mashi, and the equivalent assembly will show up here. If we well, does it, can we see it? Well, we can do simulate.
دكتور بس السؤال.
Yes, Shadi.
احنا لما كنا على مشى الكلوك بسرعة.
Here.
كان من وين اخذ الكود؟ مش من الفلاش؟
No, I meant to show you that I started the code from by clicking this arrow, green arrow. It took the code from Flash, but this, when I ran it from here, this development environment added some piece of code to configure the PLL clock, the clock, to make it to be faster. Okay, but yes, the code was there, but this piece of setting the clock speed was done by this development environment. That's why I meant to flip to the run mode and run completely from there without the CodeWarrior, and the clock was slower because this piece is not in the flash memory. We're gonna write it later on our own in the flash memory. Okay.
شكرا.
Now these are the variables we defined, right? The ports, the main function, the assembly code here. Now you can start tracking it, right? So if I want to see, for example, something here like, okay, this delay here, I can go run to cursor, see, and this is the equivalent assembly. So my delay is a jump to subroutine at a certain address, C050. Okay, where is C050? Let's go check it. C050 is
C05C صح دكتور؟
C050 is
مش 5C؟
C05C, yes, thank you. 5C, it should be somewhere 58, other 8BC. So here, so you start here. So our delay starts here, okay? And even we can go, you can do much further and go run to here, run to cursor here. Here's the equivalent code. Okay, and you can single step just like what we did there, and see now look at the left side here. You see that we are in the loop, the less than 20,000, increment, compare, increment, compare, increment, compare. Okay, then do see, you can see the equivalency code and do the computation if you want. I'm gonna stop here for this example and go start our next chapter if you don't have any questions about this code. Type. From now on, everything we're going to do is in C for me, but I'm allowed to ask you to do things in assembly. Type. Today, we're starting with chapter 6, which is about interrupts and resets. We all have an idea about what is an interrupt. Some of us had the opportunity to deal with it, and some of us read about it or took it in some class, but did not use it. So what is an interrupt? Who wants to tell me what is an interrupt? Nobody? Our TAs, I am pretty sure you guys like somebody to interact with you in class.
دكتور اتوقع ممكن هو يعني خلينا نحكي انستراكشن فجأة هيك بيدخل على الكود بغير شيء او
اوكي
هيك اللي بتذكر.
بنكون حاطين كونديشن دكتور وبس يتحقق هذا الكونديشن بيجي الانتربت او حسب كيف ماشي الكود. اذا كنا حاطين انتربت بفصل بيطلع من مثلا نحكي المين كونفيجريشن اللي احنا عاملينه وبروح على محل ثاني بيسوي محل ثاني بمشي الكود وبرد برجع بعدين بس يخلص الانتربت. انا هيك
دكتور انا بتذكر الانتربت اذا فعلته في نوع منه، اذا فعلته ما تقدر ترجع تسويه الا لما تسوي ريست.
Correct. Yes.
هو الماسكبل والانماسكبل انتربت انا هيك.
Exactly, Salah. Yes. Yes. طيب, let's talk about what is an interrupt first, and then go to maskability. So, you were all right. So, an interrupt that interrupts something that is doing something routinely, right? So you're doing something, somebody interrupted you, right, out of your plan. So the normal case for a program running on a microcontroller, the program is in the program memory, right? And there is something called the program counter register pointing to the next instruction to be executed, right? When an instruction is done, the program counter increments to the next instruction. When this is executed, the program counter points to the next instruction to be executed, and so on, right? So the normal flow is to keep incrementing. Sometimes you may find a branching instruction, right? Or a call to subroutine call. And it is also a branch. A branch instruction affects the value of the program counter, right? Write a new value to the program counter, causing the program counter to go somewhere, jump somewhere to execute out of order or go back to execute something up there, right? So branching and subroutines are instructions that cause the change of the normal program flow, which is the program counter incrementing, pointing always to the next instruction to be executed. An interrupt is not an instruction, okay? An interrupt that causes the same, but it's not an instruction. An interrupt could be a hardware interrupt or a software interrupt. But in both cases, hardware or software interrupts, both cases need hardware support. Okay, and interrupts are asynchronous, meaning you don't know when they're going to happen. A branching, a subroutine, we know when it's going to happen. It's going to happen, this branch is going to happen after this instruction. We know, right? So we can be prepared when we branch. Before I branch, I can go save my registers, do everything, branch, execute code, then go return back to where I was. But for interrupts, it is something that interrupts the normal flow of the program, causing the program counter to go point to somewhere else, execute different code out of context, okay, without being previously notified. It comes without a notice because of a button pressed, because of a door open, because of a timer expire, because, you know, so usually interrupts are caused by hardware in most of the time. Sometimes we may have some software interrupts caused by software, like when a number is divided by 0, for example. Okay, but this triggers a hardware thing that will cause to send the program counter a new value, okay, a new value, pointing it to go to a piece of code in the program memory, okay, the new value, to a place called the interrupt service routine. Bingo saying ISR, interrupt service routine. So what is an interrupt service routine? It is a piece of code. You write it just like you write a function, but you don't call it. You don't branch to it in your code. The hardware will cause the program counter to go there when something is triggered by hardware. Okay, we're going to look at kinds and types of interrupts and what will cause us to go to execute code that, and this code, what is the code? This is something you write to deal with a problem or with an interrupt with somebody that wants a service from you when he triggers you. Okay, so this is some code you write. But what makes interrupts different than subroutines is that you don't know the original program here doesn't know that it is going to be interrupted while executing this instruction or while executing this instruction. That's why an interrupt needs support by hardware to save the status of the CPU, all program registers, the return address by itself. You don't do it by code, okay? The hardware does it for you. So this is the interrupts in a nutshell. Okay, interrupts opposed to something called pulling, and we usually use it to service the things that need to use the CPU. So for example, in our microcontroller here, the CPU, we have an infinite loop, right? And let's assume we want to write code to do the following. I want to check if a button is pressed, button 1 if it's pressed. I want to turn the red, green, blue LEDs. If button 2 is pressed, I want to increment a counter displayed on a 7-segment display. Then a third task, something that blinks the 7-segment display. طيب. A fourth task, something that reads the temperature, and if it is the temperature is above a certain value, the delay value of the delay of blinking changes. Okay. A fifth task is to check for the potentiometer value and change the speed of a motor. So if the CPU is to do all these functions in a polling manner, meaning go into at the end of the day, what did we just wrote a program. What is a program? When we wrote our main function now, you want to, your program is a series of events, right? You check if button port B, and I'm going to be abstract here, is pressed, do task 1, turn on the LED. If button 2 is pressed, do task 3. If temperature is above a certain value, do task 4, and so on, right? You keep doing, you check the first peripheral, the first hardware, if it needs value, if it needs, if it's pressed, you go do something. If it's not, you go check the other thing, and you keep doing this forever. So the CPU in this case is always busy, right? This is 100% busy. Busy means what? It is fetching instructions from the program memory, decoding it, and executing it. Even if this if means that go check something, read something, compare it with something. If the result is true, do something else, do something, right? So your program, your CPU is busy executing instructions. You're wasting time. Even if none of the buttons is pressed, even if the temperature is not above the condition you're looking for, etc. This is called pulling. Okay, you pull your peripherals, your hardware components. You check your stakeholders, your people. Do you need a service? No. Do you need a service? No. Do you need a service? No. Then if when the last one is done, you go back. So here maybe a low priority task here can waste the time of everybody else. The CPU is busy. If imagine you check this button, it was not pressed, then immediately when you left this condition, this is true, this is true, this is true, this is true, then the amount of time you're going to spend before returning to this task service is going to be a lot. And this will not be helpful in real-time systems. And in embedded systems, we're usually talking about real-time system controllers, code to serve, to control real-life stuff. It's not allowed that you go turn on the AC and it takes a delay of 5 seconds, then it turns on. This is not acceptable. You start your car, then you push a, I don't know, you push a button on your dashboard, and delay happens because of other routine tasks that can wait. From here, the concept of pulling is not acceptable in real-timeness. Okay, so the concept of interrupts came up, but interrupts that are able, be there. What does an interrupt be? Say, translate into code, if you want to translate it, is that keep your for loop empty, keep it empty, or with minimum amount of tasks that you want to do. And if a button is pressed, it will trigger a hardware that will make the program counter go point to somewhere, the subroutine, the interrupt service routine, do whatever you want to do when the button is pressed, then go back, keep doing your home keeping task, So this is the main concept of what is an interrupt. So it is a peripheral, a hardware, something supported by hardware that will force the program counter to go execute some different code out of sequence.
دكتور احنا الانتربت كنا نستخدمه كمان في البي ال سيز عشان اذا صار في الريدندنسي سيستم فولت او شيء زي هيك، نفس المبدأ كان بس هو عبارة عن فانكشن بلوك.
Thank you, Ahmed. An interrupt, the very first application that brought interrupt is to respond to emergencies, fire, or something like that. But it was found useful to respond to any peripheral, to any hardware request.
كان في فانكشن بلوك اسمه هاردوير كمان انتربت عشان اذا صار في اي مشكله في الهاردوير يعني يعرف المشغل تبع الماكينه انه في مشكله.
Right. And you know, a PLC at the end of the day, in its core is a microcontroller, right?
Microcontroller.
But yeah, but it has more fancy, well-developed blocks and things like that. Here we're gonna deal with the the lower detail of interrupts. Okay. So this defines what is an interrupt. It's something that stops the CPU from normal program execution, causing the program counter to go respond to an event. The cause of an interrupt could be in a response of an I/O completion, an I/O trigger, a timeout of a timer, and legal operation, opcode, arithmetic overflow, divide by zero, etc. Okay. The main advantage of interrupts, it prevents the CPU from being busy all the time just checking for conditions. Okay. And it also provides a graceful way to get out of errors or problems or loops or whatever. Reminds the CPU to do routine tasks, periodic interrupts, we call them periodic interrupts. Here in next, they're going to come soon. We call them real-time interrupts. I want this thing to happen every second. Well, okay. Then what about what do I do in between? Well, go to sleep. And this is a really critical and important thing in battery-powered systems. And today we're talking about Internet of Things, right? Internet of Things. The things at the end of the day are what? They are computers, right? Controllers, processors running, battery-powered usually, right? And doing something specific. Well, if I want to design a system to collect the data from the weather data from all around the country or whatever, you go through them everywhere. You read humidity, temperature, I don't know, whatever you want. And the sampling is usually what? You want to read it every second? Okay, every second. طيب, a CPU running on a 8 megahertz or 16 megahertz or 50 megahertz speed, well, you read the temperature, the value of the temperature, or you do a task in, let's say, in 1% of your time. Like, what about the 99%, other 99%? Do you want to keep the CPU busy, consuming power and energy, doing nothing? You go make it sleep. And when that the 1 second expires, the hardware will wake it up and go read the new value. Okay, so these interrupts are very important. And by the way, when we mentioned the watchdog time, the watchdog timer, at the end of the day, the watchdog timer is something, it is special, but it is a timer that overflows and causes the program counter to go out of sequence, right? It sends it back to the first instruction, causing a reset. A reset is an interrupt. And that's why this chapter is called Interrupts and Resets, because a reset, when I push the reset button, or a reset happens because I draw more current from a pin, or a reset that is caused by a watchdog timer overflow, a reset will cause the program to start over, meaning go make the program counter point to the first instruction in your program. Well, this is an interrupt to the normal flow, right? That's why this chapter has interrupts and resets together. Interrupts, as Yazid said, are either maskable or non-maskable. Maskable or non-maskable. Maskable interrupts are interrupts that you allow them to interrupt your normal program execution, but if you want, you can disable them. If you're doing something really important, I don't want anybody to disturb me, okay? As if you were working in your office and you keep the door open, you're doing your normal work. If somebody walks in, he will interrupt you and you will serve him, okay, service him. But if you don't want anybody to interrupt you because you're doing something critical, you can close the door, right, and lock it. Nobody will interrupt you. These are called maskable interrupts. Okay, an interrupt that can you enable or disable, maskable. Okay. But some interrupts are non-maskable. You cannot, if you're in your office, some interrupts, if somebody has the master key, the boss of your company, he can open in his higher priority, or a fire alarm will cause all doors to open automatically. Okay, this is an unmaskable, for example. So non-maskable interrupts are interrupts that are allowed to interrupt the normal execution of the processor without getting your permission. Okay. I hope to start doing maybe let's try our goal to cover all the theory behind interrupts. Most of you know about interrupts, and start writing interrupts and interrupt service routine and running them on our board really soon. Interrupts also have priority, which means if a button is pressed or a signal coming from the alarm system comes to the controller, what is higher priority? Usually the fire alarm is a higher priority. We should respond to that, go execute that interrupt service routine that will turn off the fire, right? Not the interrupt service routine that will turn on the music. Okay, so there are priorities. How to deal with priorities, how to set priorities, we're going to look at those. But for an interrupt, because an interrupt, you don't know an interrupt service when it happens, because you don't know when the interrupt actually is going to come. You never know when somebody is going to push the button. You never know when an alarm is going to run because of a fire or whatever. You don't know. So that's why an interrupt will cause the hardware to do some stuff before doing the service routine. Okay, so not to ruin everything else on the controller. We didn't worry about that when we dealt with branching instructions, when we dealt with subroutines, because we know when a subroutine is going to come, and all what we cared about in a subroutine is to solve the return address, to save the return address in the stack. But here you don't know. Maybe I'm using A in the middle of a big or long mathematical operation, register A. Then an interrupt happens that uses register A. Then when you're done, you go back, okay, A changed. Everything changes. So that's why you need to save the context of the CPU. We call the context of the CPU or the status of the CPU, okay, the registers, all registers related to the CPU, including the stack pointer, including the program counter, which will point to the instruction where it was pointing at before the interrupt happened. Okay, so these are the steps that are followed when an interrupt happens. First thing, after an interrupt occurs, the program counter value is saved in the stack. Then the CPU status, شو يعني? All registers, register A, B, X, Y, are stored in the stack. Okay, and the program counter is stored. We said it's a separate program counter, and all other registers are stored in the stack. Then the hardware identifies what caused the interrupt. What caused this interrupt? The button, the fire alarm, the hardware should know that. Okay, after figuring out what caused the interrupt, we need to go find where is the interrupt service routine, where is the code that should be executed in response of this interrupt. Okay, where is it? What's the address of that code? So we need to resolve the start address of the interrupt service routine. Okay, where is the start address? When we figure it out, we're going to talk more about this thing. When we figure out where the code is, we make the program counter go point to the interrupt service routine, and execute the code in the interrupt service routine. When done, we return from the service routine, and the return, we know when we're done servicing the routine, we return. There is an instruction called return from interrupt service routine. This will restore all the CPU registered and program counter values we stored, okay? And among those is the program counter, causing the interrupted program to go back to execution from the point where it was interrupted. So these are the steps. Okay, talking about the interrupt vector, there is something called an interrupt vector. And we use this interrupt vector to resolve the start address of the interrupt service routine, to see where should be the code that you need to write or is written to respond to that interrupt source. So in some microcontrollers, so here in this microcontroller in the HCS12, we have something called an interrupt vector table, okay? And we're going to look at it. But other microcontrollers, some of you dealt with the 8051 microcontroller from Intel, or the PIC microchip PIC 16 and 18 microcontrollers. These their interrupt vectors are predefined. For example, in our case, at PSUT, in our undergrad, we teach the 16F, the 16F, the PIC 16F 887A microcontroller. The address for the reset address, the reset address is 000. Yani whenever you reset, your program is going to point to 000. And whenever an interrupt happens, the address is, the program counter is going to go to 004. This is a predefined location by hardware. The program counter will go, the hardware will cause the program counter to go point to address 04 whenever any interrupt happens, okay? A predefined location. In our case here in HCS12, no, it's not predefined. The address is not predefined. You can change where you write your interrupt service routine. Here, I have to write my interrupt service routine starting here, or write an instruction that will branch to somewhere where I write my interrupt service routine. But here, you can write your interrupt service routine wherever you want. But the first address in the interrupt service routine here, let's say it is 001F, for example. You go write it in a predefined table, okay? You fetch it from a vector or a table, predefined in memory, okay? So I know where to find the address of the interrupt service routine. It is always stored there. I know where it is. I can go get it, okay? It's not always address 5, but the address is always there in that closet. Go open that closet. You'll find the address. It could be 5, it could be 7, it could be 100, whatever. But I know where to find it. This is another way. And this is what we use in HCS12. A third way is to execute an acknowledge cycle to fetch where the vector is at. So you don't know where. You execute some code. The result will give you a number. The number is a location of where you can go find your starting address of the interrupt service routine. Okay. For us, when we want to program for interrupts, what do? First, we need to initialize the interrupt vector table. The interrupt vector table, we're going to look at it shortly. It's 430, huh? 430? 430. So, okay, we stop here. Steps for interrupt programming. And you know what? I'm going to write steps for interrupt programming, show you the interrupt table next time, this interrupt table, and we're going to do a hardware interrupt next time, a demo. We do it together. Do you like doing code and things together, or do you want me to record it just like when I did in the past in a flipped manner?
والله دكتور together أحسن.
Together أحسن. Okay. طيب, thank you. That's it for today. Next time we start with programming interrupts. If anybody has to leave, can leave. If you need any questions, you may stay until I stop the recording. See you next week.